Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good evening. Time to start. Okay, hold on. I have some issues with screen sharing from my iPad. I can share for a while and then suddenly it went off. Okay, let's see. So hopefully it is now okay. All right. So there's still a few of you guys left, but anyhow, those who actually came in late, I cannot do anything. I'll just start. Okay, so first and foremost, do not forget to sign in for your attendance from the link provided on Spectrum. Okay, so because we are using Google Meet, so you might actually forget to actually sign in your attendance. Please, it's very helpful, especially since the university requires that student be present in 80% of lectures before they can actually sit for your final exam. Okay, so please sign in via Spectrum. Okay, not Spectrum sign in. So that's actually a link I actually created on Spectrum, written something like attendance, Spectrum attendance for Dr. Hadi, something like that. Okay. All right. So last week, what we've looked at is like a very, very brief on how HPLC flow, okay, how the solvent flow, and parts of the major components. We didn't look at in very detail. We also looked at the basic principle of liquid chromatography. Okay, so this is just another image. If you actually just try and search for HPLC components, one of the images that you can find is this. And from here, you can actually list out, like, you know, they listed out a lot of components. And yes, it's true, there are a lot of components. And even if we are talking about a specific components, for example, the pump itself, there are actually multiple components inside there. Okay, so of course, being just lecture covering about HPLC, liquid chromatography, and gas chromatography, of course, we don't have any time to actually go and detail out every single component. And of course, we will not have enough time to actually, you know, for me to actually show you how to actually use the software. Okay, so what I did for this course, especially for the HPLC, is to actually identify some of the components which I think is more prone to error, okay, and which can contribute more to some errors, especially in your chromatogram. Okay, so if you look at here, there's 12 components or subsections for HPLC, but what we will look at is not 12 per se, but we'll just look at roughly on these 9 components. Okay, well, bus module is not being covered at all. It's just basically a serial module by which you use, it's a module to interconnect all of this system. Okay, so that's why I have a big box at the outer ring of the whole system, and then it's actually listed down as bus module. So bus module is part of the major component, because without bus module, each component of each module is not able to actually talk to one another. Therefore, you will not get your HPLC set up, so to say. Okay, so I listed down 8 important components. So you have solvent reservoir, degasser, pump, mixer, sample injection, column, detector, and waste or recycle. So what I mean by recycle here is collection. Okay, meaning that you inject your sample, and then towards the end of the day, you are able to collect them for whatever reason. So it can be for a purification purposes, or it can be because your product are very, very limited in quantity, so you want to get every single thing back. Because depending on the type of the detector, the whole HPLC system can either be a destructive system or a non-destructive system. So destructive means that the sample that you injected in the first place, the sample that you want to check will, towards the end of the day, be destroyed. For example, a simple example is mass spectrometry. So if you have HPLC MS, or simply just abbreviated as LC-MS, okay, so the MS setup will definitely destroy your compound, meaning that your compound will not be able, you will not be able to recover your compound. However, a detector such as UV-Vis, okay, because it just measures the chromophore of your compound itself, so towards the end of the day, you'll be able to recycle, you'll be able to collect every single thing, okay? So we will look at each and every module, but for today, we will just look at, if I'm not mistaken, up until number 5, okay? Even if you have time to actually continue to number 6, we will not do that because column itself is a very lengthy topics, is a very lengthy subject. Depending on samples that you want to analyze, there are various type of column that you can actually change. Of course, if you to change from one column to another, it costs a lot. So the cost can comes from the type of column itself, as you will see later. So for example, if you have a hydrophobic or more organic compound, okay, more hydrophobic compound, then the column, similar to how you actually do a silica normal column chromatography, so you might either use a silica-based column, or if you use a more hydrophilic molecule, for example, if you are doing peptides, then silica is not the best option. Thus, you will go to a more lipophilic column. So you use a C-based, for example, C18 column. Okay, so this is just 2 examples. As you will see next week, there are various different type of columns, and we will look at on how these columns are actually produced. Okay. All right, so let's move on to the topic. Actually, 2 major components of HPLC, part 1. So there's 3 parts, and it will be very helpful if you guys can actually reply to my WhatsApp. I asked you guys last week about what type of a detector that you prefer to learn. Okay, so far I have one out of 22 feedback. Okay, so please, it will be very helpful for you guys to, if, again, towards the end of the day, I'm just teaching. So if you guys want to learn about specific detector, by all means, let me know in the WhatsApp group. Then I will prepare lecture notes. I will change the lecture notes to cater the most requested detector. Okay. Otherwise, I will just, because of this one feedback that I received, I will just follow whatever is requested, which is, if I'm not mistaken, UV-Vis and mass spectrometry. Okay. So if you want to learn about something else, for example, if the company that you work at has an ELSD and you want to understand the principle behind the LSD, then let me know. Then we can cover about the column, about the detector. Okay, so we looked at component number 1, the most basic one, Solvent Reservoir. Oops. Okay, so Solvent Reservoir is basically your solvent storage area. It's not the bulk storage area, it's just a place where you put your HPLC solvent. Okay, so the solvents are recommended to be filtered. So if you actually purchase an anhydrous solvent, a pure anhydrous solvent that has a micro sieve, for example, inside the bottle, some solvent has micro sieves, okay, to make sure that your solvent is kept anhydrous. So it is recommended to always filter your sample before you actually use it in your HPLC system. Okay. Otherwise, if you just purchase the ones that are ready for use, of course, you again depends whether you want to filter it or not. It is always recommended that you filter your solvent. Okay. So there are multiple types of solvent. For those who might not know, a company. So this one comes from Merck. You can see the M logo over there. Okay, so Merck has different grades of solvent. If you are working in an analytical industry, or your company is an analytical company that does a lot of analysis using HPLC, then you need to make sure that if you were to purchase it, you need to look at that keyword. Okay, so normally just below the name of the chemical itself, there's a name, or kind of like a short description about it. So it can either be like this one, gradient grade for liquid chromatography, or sometimes you can find it as AR. Okay, can be analytical reagent. Okay, it can be for Merck. There's different names as well. Okay, so it all depends on what you want to do. Make sure you use the correct ones. So what are the differences? Sorry, it happens again. I have no idea why. Somehow today it doesn't work. It doesn't want to play nice. Just close everything. Okay, go back. Okay, so sometimes you might have the same solvent, but the solvent is CP. Okay, that's another acronym. That one means chemically pure. So a chemically pure solvent normally catered for synthesis. Okay, and it's not um, preferred for analytical. There's not much different if you look at, if you actually read out the pamphlet about all the reagents, they are not much different, but cumulatively, especially if say your sample that you are analyzing are sensitive towards perhaps metal or water. Okay, so you want to use analytical grade because analytical grades are normally very less in water content, and it's pure, free from metals and whatnot. Okay, so before you purchase, you need to make sure that you read all the um, kind of like specs. So over there, it's not clear, but no, over there it's normally the spec for the solvent itself. Okay, all right, so analytical grade, as I mentioned. Now, for the reservoir itself, so this is one of the available setup. Okay, so normally, so the, or I would say the minimum is for you to only have two holes up here. Okay, so one hole is for solvent intake. So it takes from the solvent from your solvent reservoir or solvent bottle into your degasser. That's one. And then the second intake is used to kind of like increase the pressure. Okay, so pressure release, so to say. So, but in this system, for example, the one I've shown you is normally the best. Of course, it's not the very, very best, but it's one of the best, whereby you have one line for pressure. So this one is pressure release for equilibrium. Okay, so that's one line. One line is for solvent intake. Okay, so intake, of course, going into degasser. And then the third line is for purging. Okay, so this purging is using gas. So why they use gas? Because solvents might have a dissolved oxygen, and depending on the sensitivity of your sample, for example, in my case, because my sample are normally peptides, and peptides contain cysteines with an SH group, sulfur group. Okay, and this sulfur group, as if you guys are chemists, then you know that sulfur is easily oxidized in the presence of water. So either oxidize forming disulfide bond, or it can form a sulfoxide. Okay, so purging gas, normally you will use either nitrogen or the best, and not the best, so to say, but the optimal ones, not the most expensive, but is better than nitrogen, is using helium. Okay, so you have two options to actually purge the solution, so that you can reduce the concentration of dissolved oxygen while increasing the concentration of non-reactive gases. Okay, either nitrogen or helium. All right, so these are some examples of solvent reservoir. So again, it's just a name. It doesn't mean that because the image that I've showed you guys from our lecture 1 was that the solvent reservoir is something like this. Okay, the image on the bottom right hand side, where it's set on top of the HPLC itself. But again, it doesn't really matter. Solvent reservoir is just a place where you actually kept the solvents for HPLC use. So it can either be something as simple as that, so a very tiny small space where you actually put it inside a container. Okay, so this is one of the acceptable how do I say this, acceptable practices. Okay, or you can have something like this. Okay, with another, most likely this is a purging setup. Okay, or you can have as simple as on top of your bench. Well, of course, to have the best practice in terms of chemical safety, then these two are the best option. Okay, why are these two not the best? Well, because in a chemical practice, especially in Malaysia, or probably not in Malaysia, anywhere else in the world, in first world country, normally in either Australia, UK, US, the best practice is for each solvent container or solvent bottle to be put inside a solvent capture. Okay, so or secondary containment, that's what they call it. It's secondary containment. So if you have a system like this, okay, in case if there's any solvent flow, backflow, or you actually accidentally fill up the solvent until it's very full, and then towards the end of the day, your system has the gas purge system. It will purge everything, and you have solvent spillage. Okay, if you have a containment, then you can localize the spillage, thus reducing the hazards that can occur in your either in your lab or at your company. Okay. In contrast, if you have an open system like that with no secondary containment, if it spills or someone accidentally knock it down to the floor, then that's it. Even if that person knocked it on the table, there will still be spillage. Okay, and depending on your table, for example, if your table is wood and the chemical is organic or slightly acidic, then you can cause more harm or damage to your property. Okay, so these two are the best. All right, so that's it for component number 1. Component number 2, the degasser. So the principle behind a degasser is by looking at the principle behind what is a bubble and a dissolved gas. Okay, so a bubble is normally something that you can actually see. A dissolved gas is something that dissolves but you cannot see. For example, I have a Coke over here. Oh, the Coke image is not present. Okay, so there's a Coke, and from if you just look through the Coke, what you will see is you will see like a clear bubble-free solution, right? But when you shake it, you actually get a lot of foams, a lot of bubbles. So where does this bubble comes from? Basic principle, it comes from a dissolved gas. So there's a lot of dissolved carbon dioxide in this case, in my Coke case, okay? And these dissolved gases can actually form bubbles, and bubbles are bad for HPLC system, okay? So that's the basic principle. So let's read through. Presence of bubble in liquid indicates that gaseous state coexists in the liquid. In some cases, they might migrate as a band or a layer of gases state inside the flow path. Okay, so a band or layer, meaning that it forms a bubble. Okay, so originally you don't see anything, but now it forms a bubble. So why can this happen? We will look at it. So there's a graph on the bottom right corner. So that's one of the reasons. Okay, resulting in problem with system instability, spurious baseline peaks, base noise, and so on and so forth. Dissolved gas or air means gaseous compound that is dissolved in the liquid and not visible to a gaseous state, as I mentioned. Dissolved amount of gaseous compound varies according to the conditions, such as temperature, ambient pressure, and even as affinity of wetted materials to the gaseous compound. Okay, so this is the reason. So originally, you don't see anything, you just see like a clear solution, but depending on the temperature, pressure, affinity of the wetted material to the gaseous compound, the gas can actually form. Okay, all right. So and why does this really matters? Because in the HPLC system, as I've shown previously, you can have an oven. Okay? When you have an oven, you might play around with temperature. Why do you need to play around with temperature? Because temperature can influence the illusion time of your compound. Okay, you can improve illusion time, resolution. You can improve resolution, and of course, you can shorten the whole separation process. Okay, so you have temperature, pressure, of course, just we call it SHPLC, so high performance or high pressure. So obviously, the system is not how do I say this? The system does not run at ambient pressure, so it's a high pressure because of the pump. Okay, and of course, and towards the end of the day, affinity of the wetted material to the gaseous compound. So to say, for example, if I have an amphiphilic molecule, okay, so amphiphilic molecule, you have lipids, and then you might have something like a cationic cake, okay, right? And then the solvent that you use, say for example, is aqueous, just simply water, okay, the ionized water. So what might happen is because the ion heat will dissolve in water, the lipid does not. So if, say, imagine this is your solvent, okay, and then you form a bubble in there. If you actually zoom into that bubble, so you might have, so this is the bubble. So you might have a lipid tail forming like a micelle structure. Okay, and if this happens, then obviously, if you have something like this going through your column, then the separation will be there. Okay, um, and okay, and towards the end of the day, this is just a figure showing the relationship between a pressure and temperature. So you can either have a high pressure over here, low pressure, low temperature, and high temperature. And most starting condition of a fluid system, normally something somewhere in the middle. So pressure is not too high, because if you're working at ambient temperature, it will be about, or room temperature, standard room temperature will be about 25 degrees, and standard room pressure is about 1 atmosphere. Okay, so as you change, either changing the pressure or changing the temperature, you might have an effect of absorbed gas or gas solubility increases, so you form bubbles later, easier, or gases bubbles are created and gas solubility decreases. Okay, so it plays around with how the bubbles can form. So in other words, in liquid, you don't observe any bubbles, but it may generate bubbles typically in the change of temperature or ambient pressure, as shown in the bottom right hand side graph just now. Okay, therefore, a process that is designed to simply remove bubbles present in a liquid won't help you to prevent bubbling over time. Okay, to prevent bubbling, you must remove the dissolved gases compound out of the liquid. So this is where degassing takes place. Degassing greatly improve position by degassing fluid far below the saturation point of instrument operation, so that it will remain bubble free. Okay, so simple basic principle: HPLC system does not like bubbles, so you want to remove it. So these are some of the general purpose on why you need to remove bubbles or gases, dissolved gases. Yes, the system still works, but if you actually remove it, then number one, you will be able to prevent loss of precision in terms of when you are doing a quantification or purification. Okay, so especially, bubbles, in simple terms, bubbles are bad. Okay, so you want to, as best as possible, to remove it, to eliminate the source of bubbles. Number 2, assures the accuracy of sensitivity of measuring instrument, including HPLC that deals with liquid. Again, so when you're talking about accuracy or sensitivity of measuring instrument, if you look at the bottom right hand side, okay, so these are an example, a real life data on the differences between no degassing system, helium degassing, or online degassing, where the solvent itself is methanol. Okay, so you can see the baseline for a non-degassing system is higher compared to if you actually degas it. Okay, of course, online degassing is the best, but also it's the most expensive. Okay, and number 3, prevent oxidation decomposition of compounds. So again, this is related to when I mentioned about if your samples are sensitive to oxygen. So by degassing, of course, one is by purging. So purge, you are substituting oxygen with helium gas, and then you further degas it using a degasser system. So you definitely will prevent any oxidation from occurring. Okay. And number 4, prevent growth of microorganism and algae in the liquid. Again, to the end of the day, this relates a lot to presence of oxygen. So you either gas it using a noble gas, or you remove the gas altogether, so you can avoid having microorganism or plants to grow in your solvent system. Okay, and on the graph on the right hand side shows some examples of different ways by which you can remove gas. So this is not just typically a standalone for HPLC. It can be in HPLC, or it can be like if you prepare a solvent, if say for example you have a HPLC system that doesn't have a degasser module. So what you can do, and alternative ways, is by using ultrasonic degassing. So for example, if I have in a solvent, okay, so this is your solvent, and then you have a sonicator somewhere in the lab. So because your HPLC system doesn't have any degassing module, you can simply just put this solvent inside your sonicator, sonicate it prior to your use. Okay, so that's one way to do it. So you can also have a vacuum degassing. So this is part of degassing system, a general degassing system. Most HPLC degassing module is a vacuum degassing system. Okay, we will look at it in the next few slides. You can also have helium degassing. What it does, it degas, at the same time it's putting helium in. So it's kind of like how I mentioned in the previous slide, where you have a purging system and then you have a degassing system. Okay, so you can have it there. And then the last one is where you can have a reflux system. So reflux system meaning that you actually heat up the whole thing and then just taking out a very pure solvent. Okay, so of course, if you do that, reflux is the best because reflux, you can control the temperature, you can control the pressure, and then you can get a very high purity of solvent. Okay, so this is another example from IDEX website showing you the relationship between a degassing and a non-degassing system. Okay, so the degas system is in orange, while without degassing is in blue. So if you look at the graph, okay, so you can actually see if your system actually being degassed, you get like a more how do I say this, like a normal or more similar results. However, if your system does not have a degassing system, you might accidentally once in a while get an outlayer. Okay, and this outlayer can actually come from bubblings. Okay, it forms like a huge chunks of bubble, and then this chunk of bubble can actually affect your system reading. And otherwise, you can see the range or the bell, or the yeah, plus and minus error range. So the error is huge, it's bigger compared to if you have a degas system where the results are more accurate. Okay, so this is just some of the examples on how you can actually degas system. So in chemistry, again, you can either sonicate, okay, or purging, like that one. So you just add in the nitrogen gas or helium. For example, you can just purge the whole system. Or for HPLC, you do have your inline degasser system. Okay, so just a bit more definition. So sonication, solvent can be roughly degassed by repeated sonication under light vacuum. If you do have a vacuum, if you don't, then it's still okay, it's still acceptable. For just a short while, between 30 seconds to 1 minute for a small solvent. If you actually have larger volume of solvent that you want to degas, then you need to sonicate it for longer. So in my case, I previously degas a 1 liter bottle, 1 liter Scotch bottle, about that size. You can see me, okay? And we did it based on our SOP. We normally do it for about 15 minutes. Okay, 15 minutes at the highest sonication power to actually degas everything before we actually use it. But once we had the degas system, we normally don't do it anymore. Okay, purging is the least efficient way to degas the system. However, it's acceptable for some applications, particularly with large amount of solvents needed to be roughly degas. As it sounds, purging consists of bubbling an inert gas, nitrogen or argon or helium, through a solvent for 30 minutes to 1 hour. Care should be taken to prevent solvent evaporation, especially the condensation of water in the solvent by using an appropriate setup. Okay, so this is just an idea on if you are thinking of doing it. There's two ways of doing it, or if you do have the money to purchase an inline degassing module, okay, you can actually do that. Okay, so it's very high efficient. In line with the whole system, you do not need to have a purging system, but if you do have it, you can still purge your solvents on the solvent reservoir. Okay, and it's a unique design to assure reliability, continuous operation, and highest level of continuous performance. Okay, so one module like this, last time we tried to replace one, cost roughly about 5,000 ringgit. Okay, just for this one module. But again, if you purchase like the whole HPLC system, then perhaps you'll be able to get it for a cheaper price. And that was 2 years ago. Due to MCO and the change in our economy, I'm not sure what's the current price. Okay, and the basic system is like that, where you have your solvent reservoir here. Okay, so each solvent will go into a vacuum chamber inside the vacuum degasser system. So that one, this box is represented by the outer box over here. Okay, where you have inside there, you have another vacuum chamber, so like a vacuum bag, and you have a different membrane in here. Okay, so these are all membranes. It's not the same type of tubes like this. Okay, so they are different. So this tube, the ones that I'm drawing now, is similar to the ones outside, but everything inside has a different tube. Okay, so we will look at that in a few minutes. Okay, so this is where a vacuum is being turned on. So inside there is a vacuum. So any dissolved gas will definitely go out from the system as long as your vacuum chamber is working fine. Okay, so that's another image to represent the vacuum system. So each line, each inlet and outlet, you have a vacuum chamber, and thus you have all this system by which all dissolved gases will come out from the solvent. Okay. Right, in gas, inline degassing, in online or inline degassing system, inside the unit, the solvent flows through a short length of Teflon AF tubing. I think I have a picture of that. Oh, I didn't. Okay, so it's a different tubing. It's not the same tube as you normally use to connect all the modules. Okay, it's slightly different. It's like a rubber, so to say, but it's definitely not rubber because it's chemical resistant and whatnot. So it is actually made up of Teflon. Teflon is um, one of the highly chemical resistant um, polymers. Okay, it's located in the vacuum chamber. So which is that one? So that one in there is the Teflon. So the one outside here that connects the system again is something else. Okay? It might be Teflon as well, but it can also be different plastics. Within the chamber, a partial vacuum is maintained by a constantly running vacuum pump. Again, basic principle. Dissolved gas migrate across the tubing wall as a semi-membrane under a concentration gradient reduced by the vacuum as the solvent flows within the coil. Okay, so it's a basic principle. If you have even a constant pressure inside here as the solvent flows, then your dissolved gas will go out, and towards the end of the day, you will have rather a solvent-free, solvent-free, solvent that has that is free from any dissolved gas. Okay, that's the correct word. Sorry, I'm a bit tired because I just finished my lab. Okay, so simple membrane. What else do I need to talk about here? So these are just an image on your connection that is being shown up here. Okay, that's one of the connection system for HPLC, especially in connecting to the a degasser system. All right. So next one, someone wants to ask something. All right. Okay. So next one is the pump or solvent pump, whichever you want to call it. Okay. So why do I still have this? I'll just skip. Okay. So a pump system, if you think about it in a classical system, when you're talking about column chromatography, which has similar principle to HPLC, you normally do not use pump. Yes, you can use pump. In some system, you can actually use pump, but the basic ones, especially when you are learning during your undergraduates, normally you do not use any pump, because when you use a pump, then there are multiple things that you need to watch out for. Okay, in a classical open column chromatography, the old ones, okay, the mobile phase flows through a bit of column packing. Because of gravity, this work barely with large particle size, but separation times can be extremely long. Okay, so because due to gravity, again depends on the silicon that you use for your separation. So it might take a longer time, and some might be faster. Okay, and on the quantity that you use, the length of the column, the length of um, the total length of the silica. Okay, so all of these influences the time of your LC run, liquid chromatography run. Okay. So in order to reduce the separation time and allow to use for a smaller particle size packings, okay, so you want to use the smaller ones because you then will have a better interaction between your compound and your solvent system. Okay, we must force the liquid to pass through the column under pressure, under high pressure. So the smaller the particle size, the higher the pressure. Okay, thus you need to push. The smaller the particle, the slower the flow. I'm thinking about flow, but I said something else. Okay, thus you need the pressure to actually to help the system to push through the solvent going through the column. Okay, this is the function of a pump, the solvent delivery system, to maintain a constant flow of high precision and accuracy of mobile phase through HPLC, regardless of the pressure or back pressure, that's the correct term, caused by the flow resistance of the pack column. So if you put a pressure in here, So due to the tightly packed system, you always have a back pressure opposing the pressure that you are putting in. Okay, so common particle size for HPLC packing is between 5 to 1.7 micrometer, but I think now I've seen 1.3 microns in size, so it's getting smaller and smaller. And of course, as it gets smaller, the separation is better, and depending on your whole setup, you can actually save time. Solvent flow modules pump are required to deliver a pulse-free flow. Okay, so what do I mean by this? So imagine if you have a pump. Okay, so a pump is a piston that pushes through in how do I say this? It's like a piston in the engine, in a car engine, right? So um, a piston just moving back and forth, and this creates pressure. So if without a free flow pulse, so what you will get is as the piston moving back and forth, you'll get a pressure going up and down. Okay. So why up? So increase in pressure is when you have a space. Okay, so imagine that the size of my head is a space and the piston is originally at the middle, at my nose. As it compresses, so you get a higher pressure, and then as it reduces back to its original location, then you'll get the zero motion here. Okay, and then when it moves to the back, then you go to the negative value. So without a pass-free pump, then you will get a sinusoidal curve, and what this happens is that it will affect your flow. The flow of your solvent system must be constant, because if it's not constant, then you can get like your retention time is not repeatable, replicable. So there's a lot of issues, especially if you're doing an analysis. Your lab is in an analysis lab, and analysis looking at quantity and quality of your sample. Okay, so having a good flow rate is a must for that particular company. Okay, so continuous flow of 11 to the column at the flow rates ranging between 0.1 to, well, it doesn't have to be 10 mils per minute, with precision of 0.5% or better. So again, the volume, the upper limits and the lower limits, depending on the system that you're using. If you are using a UHPLC system, then yes, perhaps you might want to use an even lower flow rate, perhaps 0.05 mils per minute. And depending again on whether you're working in an industry that does a lot of purification, you might use like a bigger HPLC system. And the ones that I've used previously can pump up to 100 mils per minute. Okay, so not just the pumps is bigger, but the column itself must be big as well. So imagine if you have a column, it's size of this pencil, it's very tiny. So that's the outer surface. But if you're thinking about the internal diameter of the column itself, which is very small, okay, and you have a very huge pump, a pump that can push 100 mils per minute, then definitely, because the internal diameter is very small, thus you will have a very high back pressure. Okay, so in order to reduce your back pressure, then you might have a bigger column. And the column that I've used previously, so this is a 1 liter Coke bottle. Okay, so the column that I've used previously is roughly like slightly bigger than this column, this Coke. Okay, so then you can have a very pressure, a very flow rate, a varying flow rate, and thus it must be accompanied by a different types of column. Okay, so the main criteria for a suitable pump can be summarized as below. So it's just some keywords that you need to think about. So so the material construction must be inert towards solvent use, meaning that there's no reaction. So the best is, of course, if you have like a Teflon base, but of course there's no Teflon base pumps, none that I know of. But you must be in it, two chemicals. So that if you were to change your chemicals, if say one day, on day one you want to use methanol, and then day two suddenly you want to use hexane, day three you want to use acetone, day four you want to go back to water or plus an acidic solution or a basic solution. So it must be in it towards this various type of solution. That's the best, of course. So a pump must be capable of delivering high volume of solvent. Again, this is depends on the usage. Okay, so if your usage is more analysis, then if you are thinking about doing analysis using like a very micro column, okay, or flow flash column, very tiny, very small, it's about that size, then perhaps you want to have a system that can run until about 0.1 or 0.2 mils per minute. But if you have a bigger column, you want a system that can give you the best flow rate as possible. Okay, it should be capable of delivering a precise and accurate flow. Precise flow just refers to if you want 1 mil per minute, then if you actually measure it, you can measure the flow of the solvent coming out of the pump, then it will be 1 mil per minute. If you want it to be 2 mils per minute, then what you the illusion, if you were to measure it, you want it to be 2 mils per minute. Okay, and an accurate flow meaning that either accurate lah. Okay, so precise and accurate. If say for example your pump, originally when you purchase it, it's very precise, it's very accurate. If you set it to 1 mils per minute, then it will be 1 mil per minute. If you set it to say 5 mils per minute, then if you actually measure it using either measuring cylinder manually or use a syringe and whatnot, you do get it 5 mils per minute. But say after a month, when you redo your preventive maintenance, then when you check your flow and then suddenly the flow becomes 4.5 mils per minute, then you know something is wrong. Okay, so it can either be the pump itself or the damper, as you will see later on, or it can also be a bubble in the system. Okay, so if you have a bubble in your pump, so then the compression when you're talking about this sinusoidal graph, okay, so you might have a reduced pressure like that. Therefore, the output of the pump itself is reduced. Okay, so these are some of the criteria. That's why I just put it there so that you guys, at least know what to look for in case if something like this happens. Okay, so we will revisit this phenomena or this example when we're talking about troubleshooting HPLC. Okay. The pump head should have a small volume to facilitate rapid change of the solvent composition. Okay. Solvent composition is also very important. But again, this one depends on the type of pump, the whole setup itself. If, say, you have a single pump, and then towards the end of the day, the pump will flow through into a mixer, a separate mixer, then the pump itself is reasonably okay, even if it doesn't facilitate a rapid change of solvent composition. Okay. It should be capable of delivering high pressure up to about 7,000 psi. Again, this one depends on the pump itself. This all values refers to my normal usage. Again, normal usage, my abnormal usage is something like that. So that one is abnormal. But in normally if I were to run HPLC, then this is the range. Normally it's not even down to 0.1. I normally run between 1 mil to 10 mils per minute, depending on what I'm planning to do. Okay. So delivery pulse, and it should deliver a pulse-free flow, hence not contributing to detector noise. Okay, detector noise, pretty much why we call it as detector noise, because it will affect your sample reading. Either your baseline is either increasing or decreasing, or or if there's any bubbles present without high pressure, the bubbles might actually stay inside the detector, thus causing an error in your reading. But if your pump is well taken care of, and thus it works how it intended to be, then even if there's any bubbles, then the bubbles can easily go out from the system. Okay. All right, so most commercial HPLC pumps are based on reciprocal piston design. So as I mentioned, it's like our engine. Okay, so a car engine. So it's a piston, same principle, but the inlets and outlets are of course different. For a car engine, the inlet is either gas and petrol. The outlet is just gas, okay, exhaust gas. Oh, sorry, there is an overlap. A motor-driven cam pulls the piston back and forth and move the piston head. Okay, so piston head. That one. A flexible seal consumable around the peripheral of the piston prevent leaks of mobile phase out of the back of the pump. Up here, so there's no leak behind the pump. Check valve mounted on the head, open and close in response to a small change in pressure to maintain one-way flow of system. So this is how it's represented by the moving GIF down at the bottom. So cam is push on sapphire piston back and forth. When the piston is moving backwards, it sucks the eluent through the inlet check valve. So you can just read it. So basically, it just talks about how the solvent flows. Okay. When this one is open, what happened? When this one is closed, what will happen? So basically, this one is going out. That one is going in. So if you look at it, you can actually see when the piston move to the back, then the bottom ball actually opens the bottom inlet check valve. Okay, so you can have a solvent flowing into the pump itself. And when the piston moves forward, compressing the liquid, so the bottom check valve closes while the top check valve is open, so that the solvent can flow out. Okay? But imagine if you have a system like this, then if you're looking at the pressure will be like that. Okay? Because you always have an on and off. So when it's on, then this happens. When it's off, another thing happens. So basic principle. So what do you need to have? What else you need to have in order for you to have a free flow? Then you need to have, probably next slide. Okay. So this is, I mentioned, the flow increases from 0 to maximum and then back to 0, blah, blah, blah. The same thing, the kind of flow is shown above, where the flow rate changes during the pumping cycle causes pressure pulses. Okay, pressure pulses, as I mentioned. It's more sinusoidal. Okay. All right. Pulses are undesirable because of they cause detection problems, back and forth. So say, for example, if you think about if my my right eyes over here is the detector, okay, and then you have a sudden increase in pressure, and then low pressure, and then high pressure, and then low pressure. Imagine if you have say a sample that you want to analyze that move through the column and move through the detector. So under high pressure, you might move very, very quick. And then under a normal flow, it slows down and then move quick again and then slows down. So the detector might actually detect like a very huge peak or a broad peak. But perhaps if you change to a better pump, you'll get a more uniform peak. Okay, so that's one option. Prevent good quality analysis, of course, is related to that. Leads to earlier column failure. Okay, so earlier column failure because columns, how do I say this? Likes to be in one condition. Okay, so if your column you want to use with acetonitrile, for example, acetonitrile and water, so sometimes it's not that good to keep on changing your solvent. Okay, so there are multiple reasons why you can't simply just keep on changing your solvents for a column, but we will look at it in the future. Okay, and the column, so perhaps next week. All right, so to overcome this problem from one piston, so again, the pressure pulse is due to one pump system. So you can overcome it by either one having a dual pump system where it complements one another. Okay, so instead of having a normal pulse, normal pulse, and then high pressure, normal pulse, high pressure, normal pulse, high pressure. If you have a dual piston system, you can do, of course, we don't create our own pumps. Okay? We normally purchase it, but in case in the future you actually someone donated to you one single pump, it can happen. I'm not saying that it's impossible. It can happen. And so what you can do is instead of purchasing a dual pump system or a better pumps, so you might want to buy a single pump piston and then set it so that it complements one another. So imagine if the second pump has the opposite movement as the original pumps that you have. So if you combine these two together, you will have roughly something like that. Okay, so it's more constant rather than of course it's a higher pressure. It's the combination of this over here and not the ones at the baseline. Okay, but you will have a more um, better flow, a better constant flow throughout your system. So dual piston pump provides a constant and almost pulse-free flow. Okay, both pump chambers are driven by the same motor through a common eccentric cam, so it's just a opposite direction. Okay, and since each head has two check valve, pump reliability depends on the cleanliness of the mobile phase and continued sealing capability of the four check valve of each cycles. Okay, so as I mentioned, it's just a complementary. All right. Additionally, what you can have is to purchase another type of system, which we call as a tandem piston pump. Okay. So in contrast to either the dual piston pump or a single piston pump, where you have the exact same pistons size, tandem piston pump is like a complementary to one another, whereby one has a bigger volume than the other, and at the same time you have a check valve between these two pumps. So tandems mean one after another. So instead of having two pumps, so you have a tandem that solvent flows from one to another. So dual piston pumps with only two check valve, piston volumes are different, can be different size or same. While the smaller piston dispense the eluent in the HPL system, the bigger pumps is sucking the eluent. When piston changes the direction, the bigger piston simultaneously refill the smaller chamber and dispense the eluent to the system. So it's kind of like a complementary system as well as a two piston pump. Okay. Do I have a picture over here? Okay. So that is an example of, wait, not this one. Sorry, not this one. We actually do have a tandem pump in UM. So perhaps if I do have time, then I will do like a very short recordings and show you guys. If I'm mistaken, it's a piston pump, a tandem piston pump. Okay, so you can actually see two kind of like button moving, not button, it's actually the piston is actually moving back and forth within the pump. So imagine that if this is the pump, you can actually see I recall it's something somewhere like that. So it's moving back and forth, but one of the piston pump actually move faster than the other. Okay, just to complement. So that's an example of piston pump. Perhaps if I do have a recording, that I will post it so that you guys at least have a rough idea on how it works. Okay. So this is just an example of pumps. You have Shimazu pumps. This one is still a Shimazu, so everything is a Shimazu pump. Of course, looking at the images, some of them are rather old, some are quite new, so to say. Okay, but again, just based on the number, you can see either it's a single piston pump or a tandem piston pump. or a dual reciprocal piston with highly stable, blah, blah, blah. Okay, so this is just the definition or the information related to the pump. So I just took it from the company itself that talks about the specific pump types. Okay, just put it there. Just an extra info, nothing important. Okay. The pump cylinder with its check valve is often accessible from the outside to allow easier servicing of the check valve and replacement of the pump seals. So that is the pump, the cylinder pump. And if you actually open it, then you will see this. So one is a filter. So you can have a filter. And then this is the, what do you call it? Seals. Okay, a seal or for cars, what do you call it? That thing that you put in the engine. I can't remember. I can't remember on top of my head. Okay, so there are common consumables. However, they are not cheap. They are rather expensive. This frit, okay, is the size of, how do I compare that so that everyone have an example? So if you take a 10-cent coin, okay, which is about that size, this filter over here is roughly about 2 millimeters or 2 to 3 millimeters. Okay, so about like, so it's very tiny. So it's actually very small and it's very expensive. One of that last time when I replaced it cost, it was in Australian dollars 10, so about 40 ringgit, so to say. It's very tiny, it's very small. Why? Because this is not a normal filter. This is a metal frit, so a metal which has holes in it. Okay, so perhaps that's one of the reasons why it's expensive, or perhaps this is how the company makes a profit. Okay, of course you do need to have it in your system. Why? Because say for example, if your solvent is not clean, okay, you did not filter it. So that's why I put a suggestion at the very beginning during the solvent reservoir is for you to have a filter. So you need to always filter your solvent because sometimes you do have some particles inside your solvent. So the particles can either be, if your solvent is from a glass bottle, so the glass might chip and then forms all these very small tiny particles of glass that can enter your system. Okay, if it's just enter the system doing nothing, is okay. But imagine if you have a particles that cannot dissolve, it passes through your column, and again the particle size in your column is very, very small. Thus the void volume of your column itself is very, very small. Even if you have a small speck of dust going into your column, as it builds up, one day it will block your column and therefore you cannot use it anymore. Okay, and column is very expensive. One purification column like that huge, it's very small, it's not even one module, costs about 10,000. Okay, the good ones, of course. If you just want to buy cheaper ones, then yeah, you can get it for a cheaper price. But the ones that I normally use is the one that can hold high back pressure. So it is normally made of stainless steel and it costs a lot. So $20,000 ringgit, 20,000 ringgit, not dollars. Okay, so for you, if say you need to replace a column in comparison to just replacing this one frit, then of course replacing the frit is cheaper. Therefore, throughout your system, normally you have multiple frits or filter that filters out whatever solid particles that are present in your system. Okay. So common consumables, you have your piston seal, you have your solvent frit or check valve, and problems in the pump that you can encounter is leaking. Okay, so if it leaks, it will affect your reproducibility. It might affect your peak height because if it leaks at the area where your sample is going through, Okay, so your sample might actually leak out from the system, thus you are wasting your sample, and therefore you will have a lower peak height. Okay, so it will thus affect your peak height. And of course, if you do have a leak, depending on the degree of the leak, it will either slow down the pump, and if it does slow down the pump, then it will definitely affect your retention time. So what's the issue? The issue is if, say for example, you do not periodically run a standard sample in your HPLC, and then one day you want to run, but there's actually a leak, and it affects your retention time, and thus instead of, so say for example, if you have a standard like that, okay, but one day, so in normal scenario, you might have a sample peak like that. So this one is sample one, so it's standard, okay. So if say your pump leaks, your retention time might be lower, okay, or higher retention time because it stays longer in the system. So it might, even if you're using the same sample, so the sample peak might come out after your normal standard. So you might say, oh, it's no longer there. Therefore, if it's about disease, then you can say, oh, this person is actually free from X and X disease. While in reality, it's because the improper management or you're not running a preventive maintenance, for example, and that's affecting the performance of your HPLC system, affecting the results analysis, and therefore you can actually affect human life. Okay. So just another example, different types of pumps. You have isocratic pumps, you have a binary pumps, you have a quaternary pumps. So quaternary just means 4. You can actually intake this. You can actually intake 4 different types of solvent. Okay. So individually, meaning that you have 4 pumps, then each pump takes a different solvent. Solvent A, solvent B, C, and D. Okay. So even without a quaternary pump, if you have a binary pump plus a mixer, you can have A and B going mixed together, and then another system where it mixed together before it actually flow through your HPLC system. That can also happen. So doesn't mean that having a quaternary pump is always the best. Again, towards the end of the day, it depends on your budget. Okay? Isographic pump is the most basic pump which has one solvent channel, so just one. So that's isocratic. So isocratic flow where you only have, say for example, if you prepare acetonitrile in water or 90% acetonitrile in water, so you have the same solvent system throughout your run. So that's when we call it isocratic flow. So you can have isocratic pump where you only have one solvent channel. So only one type of solvent can go into the system. So binary, as I mentioned, you can have 2 solvent mixing together and going into the system. Quaternary, you can have 4. So far, in my experience, I only used up until quaternary. I have not used, if there's any different pumps, I have not experienced in using different types of pumps. So binary pumps, how does it work? So you have a tandem pump. So like a single piston pump, a tandem is where you have 2 of them, 2 of the pistons working as a single pump. Binary pump is where you have 2 different pumps. Okay, 2 individual pumps that in one box. 2 pumps in one box. So each pump can have an intake of its individual solvent. Okay, so you have a solvent bottle colored in red, and then you have another one in blue. Okay, and then it's mixed. You have a pump with a mixing chamber, and it will flow through a damper. So this damper function as to make sure the pressure is roughly consistent. Okay, even if you do have a piston, a tandem system like this, and then you have a binary pump, you might think that might be enough to get the pressure to equalize throughout the system. But having a damper actually helps even better. So this is another indicator. Perhaps if you have done your servicing in your pumps, There's no leaks. Everything is perfect when you test it individually. But then when you run the whole system, you can see the pressure is going up and down. So one of the reason is now could be attributed to your damper. Okay. So binary pump module consists of two independent pumps for both solvent channels, which unites in the mixing chamber, which is followed by the damper in the secondary mixer and a purge valve. The composition of the resulting solvent is defined by a different flow delivered by both solvent channels. The composition of gradient can be sent at the range of 0% to 100% and has a higher precision. So this is the kind of like rather common HPLC setup where you normally use a binary system. In my case, the ones that I normally use is just acetonitrile in water. You might also use methanol in water, maybe not the best. Hexane in ethyl acetate, okay. So there's multiple systems that you can actually use, and this system, it all depends on what type of samples you are trying to run. Okay, so you might also have what do you call it? Never mind. Just three examples is enough. You do have a lot more, and if you actually read the literature, so you can actually try and find what solvent system have people used outside, especially if say you have an unknown sample that you want to run, but you do know the unknown is perhaps comes from a plant source, for example. Okay, so you might want to try and find a literature and look at how other people are actually doing or run their system in the solvent system to make sure that you know, for one thing, you want to use the same solvent system as what other people have been used, so that you can do a direct comparison. Okay, so say for example, if in my case I've used a peptide, if say the peptide names is J14, so I might want to use I might want to go to the find a resource from other people that have published with regards to J14. So like for example, J14 is a peptide that I've used way back when I was doing my PhD. So my supervisor might still use it. So if I were to do the same system to try and either synthesize or purify the same peptide, J14, here in Malaysia, so what I might want to do is first to just exactly copy the methodology that is being used by my supervisor. Okay, so if the supervisor is using acetonitrile and water, then perhaps I want to use the same system so that to the end of the day, I can do a direct comparison. Because again, you need to remember LCMS is nothing without the detector. So if my detector is an MS detector, then perhaps even if the retention time is different, but as long as the mass is similar, then I can say, oh, this there's a high chance that this is also J14. But say, for example, I'm using a more universal detector like UV-Vis. So if I have a different retention time, then it might suggest a different peptide, not J14. Okay, so that's another reason why sometimes you want to find literature information first before you actually run your first sample. Okay, so and gradient is very important to make sure that you'll be able to separate your sample of interest and the non-unknowns and the byproducts. For example, if you're doing a synthesis, okay, so why can't you use isocratic flow? Then you can use it, but isocratic flow is normally takes longer in comparison to if you are doing a range analysis. Again, it depends on the solvent system that you're using. So if you were to say use isocratic flow using hexane, it might be better than using a gradient range for isonitride in water. Okay, so at the end of the day, it depends on your sample, column, solvent system, and so on and so forth. So there's no one system that fits every single sample. Okay, so that's why back in our first lecture, when you're looking at the plot of different names of samples and whether you want to use GCMS or GC system or LC system, I always say that you can actually run everything in LC system. Why? Because depending on you can always change the solvent system, you can always change your column, then you can actually measure every single thing. Okay, but for your GC, you can't, because towards the end of the day, it all depends on whether your sample is volatile in the system. If it's not volatile enough, then you definitely cannot use GC. But LC is a different story. Even if it's a volatile system, a volatile sample, but if you can find a match, a solvent match that can dissolve the volatile compound, then you can simply run it on HPLC system. Okay, a damper. So this is a specific slide for damper. Reduces pulsation by compressing fluid held by a chamber in a unit. This fluid is isolated from the mobile phase by a durable but flexible inner diaphragm. Okay, so that's the damper, that's the diaphragm. Diaphragm. As system pressure increases during the pump delivery stroke, fluid in the chamber is compressed. When the pumps begins to refill the stroke, the compressed fluid expands, keeping the mobile phase flowing at nearly constant rates and maintaining system pressure. Okay, so that's one of the function of a damper. This is why if you consistently service your pump, your pistons as specifically, but then one day the pressure is inconsistent, then perhaps your damper needs to be replaced. Okay, so that's all for component number 3. Move on to component number 4, which is the mixer. Again, it's a very simple system. So different from isocratic or binary pump. So isocratic, as I mentioned, is just one flow. So you don't need to have a mixer. Well, perhaps you do still need it somewhere, especially if you have a sample. But normally your sample is very relatively in a small quantity compared to the solvents that you're using. So normally you do not have a mixer like what we're talking about. So that might be a different mixer altogether. Okay. So and in comparison, in contrast to a binary pump where you have 2 pumps and then you have a mixer in the middle, so you can actually mix them together. Okay, so mixer here is when you have a single pump with a tandem piston system. Okay, so multi-channel gradient valve MCGV is the device that controls the proportion of mobile phase going into your system. Do I have it here? I don't have it here. So MCGV located upstream of the pump. It features 4 inlet A, B, C, and D, and 1 inlet line which connects to the pump. Okay, so that is where you have your solvent from bottles up here, and then you have a mixer that actually controls what percentage of solvent should actually go into your pump. Okay, so this one is, I guess, after or before it goes to the piston. It might be in the same component of the pump itself, but it can also be a different ones. In my case, the ones that I've seen previously, or the ones that we have in ChemSU, at least one of the HPLC system that we have, actually has this particular system. So it's a single pump with a tandem system, and it has a mixer. And then if you actually follow the lines, you can actually see it goes to there, right? Perhaps I don't have the picture over here, but maybe I can show it to you guys. Because I'm planning to do a round on HPLC system, looking at all the system, just recording it and let you guys view it. Okay, so that is the MCGV system on the left hand side. Ensures the intake stroke piston containing specific mobile phases. The flow of each mobile phase is controlled by a solenoid valve. Okay, solenoid is a magnetic control valve. Okay, which is activated by the board according to the valve program by the user. So normally you will hear clicking sound. Okay. If you have used one, then perhaps you might notice about the presence of a sound. It's not from the piston. It's actually from the mixer, like moving and either opening and closing the valve. Okay. So this is one example, and I will show you a more like a real life example, hopefully by next week. Okay. And a more recent technology by Agilent is by having this, what they call as Agilent jet weaver mixture. So in comparison to MCGV, what it does is you only have like a one flow rate. Okay, for example, just one like that, and then you have another one over here, another one over here, another one over here, and you have 4 solenoids that covers and open and closes depending on the system that you set. Okay, but in Agilent Jetstream mixer, it has a different types of system, but at which highest mixing efficiency with the lowest dead volume, employs a multi-layer microfluidic design to ensure optimal suppression of residual composition of disturbance. Typically, application might be high throughput method with fast gradient on resolution 1.2, 2.1 millimeter column with moderate baseline. So what you might have, I have a picture of the system here. Okay, so what you might have is you might have 2 inlets or 3 inlets or maybe 4 inlets at this particular point. Okay, and then instead of having a valve, a solenoid valve that controls open and close, you might have a pump that controls whether to allow solvents flows or not, but the mixing itself occurs in this manner. Okay, if you look at the image, it's like every single thing is mixed and then is further divided. So this is a microfluidic flow system. I'm not going to go into very detail because I'm not an expert in this microfluidic. Perhaps if we call some chemical engineers, then perhaps they know this information better than me. So this is just for me to share with you guys what are one of the current technologies that is available. In case if your company is actually looking to purchase a new HPLC system, then at least you are more knowledge, or you do know more about what are the current technologies that are present. Okay, so what is the main advantage of having a jet weaver mixture instead of a solenoid or MCGV system is that you have a solenoid. Okay, so one thing is a magnetic, it's electrically controlled, and there's movement, okay, open and closing. So in a normal fashion, when you have something that can move, especially it's a very tiny component, there is a prone to damage. Okay, so having a system that does not have a mixing system or valve moving parts, then you can definitely reduce the risk of needing to spend more money to replace a component of your HPLC system. Okay. All right, next one. I think this is the last one, so we still have a lot of time. Component number 5 is the sample injector. Again, sample injector is a very straightforward system. So sample injector is over there. So there's 2 types of, well, I've seen 3 different types of sample injector. So one is manual. So manual, meaning the picture of a manual sample injector is like this. Okay. So why do I call it manual? Because you will need to inject the sample on your own. Okay, so that's a manual. And the other 2 is automatic. So number 1, automatic, is where you have an arm and I have a picture right here. Okay, so an arm like that, okay, somewhere in the middle there, or somewhere in the middle here. If you have used an HPLC before, then you can see that there's an arm moving either to take the vials and moving it somewhere else, or the arm itself is where it has a needle poking through it. Okay, so either that, so there you go. That's a system where you have an arm picking up a sample, moving it into a needle position over here, and then this is where the needle will suck the solution from the vial and inject it into your HPLC system for your run. Okay, or you have a different ways. You have a different needle here by which the arm itself move with the needle, and then it's just poking through all the samples one by one, and straight away injecting the sample into the sucking in the sample into the HPLC system. Okay, and these two are automatic. The first one that I've shown here is a manual system. Okay, so valve injection of a sample is now the preferred technique or in HPLC. Sample application is rapid and the solvent flow from the pump does not have to be stopped. 6-port valve, so this one is a 6-port valve. Okay. With external sample loops are commonly used. So this is what we call as the external sample loop. It's that one over there. It's this guy. And you can see here, if you look at that picture, it says 20 microliters. So this is the quantity or the amount of sample that this system can actually hold. So it might be the same injection sample, but you can actually replace this with a bigger sample holder. So you can go, the one that I've seen previously, at least in my lab, we do have the 200 microliter ones. Okay, and I think we do have like 1,000 microliter. That's the biggest that we have. Like there's multiple loops behind it, but everything else, all the other components at the front of the injection valve are similar. Okay, so this is the viewpoint on the rotary knob. This is again just information for you guys. It's very straightforward. So basically, in a load, there's 2 positions. So you can actually move this handle. Okay, this handle can be moved into a load or an inject position. So there's 2 options, A and B. Okay, so under load position, what you will have is you have the solvent flowing just directly from the pump into the column, okay, bypassing the sample holder at the back. So in this load position, what you will do is you will take your syringe and you actually inject it at that hole over there. Okay, so you put it in, you stick your needle in, and then you inject. So what will happen is you will transfer the sample into this middle sample holder, and then once everything is ready, you just change the knob position from load to inject, and what will happen is the loop inside the injection port will change, and thus the flow from the pump will flow through the sample holder first and then go into the column. Okay, so basic principle is just moving a knob. Okay, so that's another example. Okay, so basically it's the same. So if you want to study, you can also study this one. The difference between the load position and the inject position. Right, so and if you do have a system by which you need to manually inject your sample inside your HPLC, inside your injection loop, okay, so you need to understand there are multiple needles that you can use. So the top one is where you might have a glass needle, and the glass needle doesn't have any Teflon tip plunger. So that one is a Teflon tip plunger. So what might happen is that some of your sample might actually go through around the syringe. So what it means is that if, say, for example, you want to inject just 100 microliters of sample, or probably less, or probably 10 microliters of sample. Okay, so if you want to do that, it's best to actually use the gas tight syringe with Teflon tip, because this is very, very accurate, and you can transfer, I would say 99% of the solvent that you are planning to transfer. Okay, and additionally, the tip of the needle that you use, even though I still call it needle, it's not a sharp tip like this, okay, but it's rather a blunt blunt type needle. Okay, so make sure that if you do have this system, you should never use a bevel tip, because this can actually damage there's an O-ring inside your injection loop. Okay, if you damage it, then solvent can actually leak out from the injection loop. Okay, so that's why we normally use bevel. So one reason is because you don't want to damage the plunger, the seal in the sample injection loop. Then second one, if you have a bevel like this, imagine when you actually injecting your sample inside here, because there's no direct contact with the sample holder, so some of the sample might actually backflow, and thus you will lose a little bit of your sample. Okay, if you just lose it because you have a lot, it's still fine. But imagine if there's multiple person using the same system. So in the morning, you are the ones using it. You use a bevel tips needle to inject your sample, and so you know that you might have contaminate the injection loop because you are using bevel system. So your sample might be around the injection loop, okay, injection port. Then in the afternoon, another colleague of you wants to come in and do the analysis using a manual injection as well. And because you have contaminated the system and the other person doesn't know, when he or she runs the system, then you might get a variable reading. Okay, so it might affect your company lah, basically. Okay, so that's the general idea. Oops, so I want to change. Okay, so again, this is just an example of an auto injector system and whatnot. Okay, I will try my best to actually do a recording and show you guys, instead of just a still image like this, and a video on what are the components and the system on HPLC. Okay, so aspiration and sample injection process. So this one is just bubbling and whatnot. It's a very different types. So these different types is based on this system over here. Okay, a system by which it carries a sample might have a different system than the ones that directly inject the sample. But normally what will happen is if you have used one system, is that the needle will move into the position of your vial, will puncture through your the cap of your needle, punch it through the cap of your vial, and then it will take up a little bit of solution. Okay, and then it will go into a different place, a different location, by which they might do a sample aspiration. Okay, just bubbling some of the samples, and at the same time cleaning the needle tip before actually injecting the sample into your system. Okay, so this is just an example. Again, you can see this 6-position flow valve, whereby it can change depending on what type of process is being run. Okay, and I think that is all for today. So it's only like about slightly more than 1 hour. Okay, so you have up until 8:30. So normally I said 7 to 7:30 is your break time, and then you have 1 hour, right? To we can either continue the lecture or do a tutorial. So today, what I have is I want you guys to do your first tutorial. We should have done our first one last week, but that's fine. Okay, so the tutorial goes like this. Okay, I will post this specific slide on Spectrum as well after we finish like this, so that you can actually view it again, or if you guys are around, you can just, well, probably I will just post it on the, our WhatsApp group. Okay, that will be easier, so everybody can view. So your task is to so there's a template file provided on Spectrum. So if you click on the if you open Spectrum and then go into our course, under the lecture notes section, there is actually a place where you can submit a tutorial. If you click on that, you open the Google form, and then from the Google form you can actually download a template. Okay, so there's a template file that I've already created and provided for you guys with all the correct formats and whatnot, so do not change it. Okay, so I want everybody to have the same format. Okay, so and write no more than one page. So maximum of just one page. Do not change your font size. Do not change the different font. Do not change the page size and whatnot. Okay, just use the template. Just key in your answer. Okay, you may include the picture, or pictures to support your argument. And you need to submit it by 8:30 today. So part of the tutorial is you'll be doing it. Well, you can do it as a team after this if you want, or you can just do it individually. Okay, and you will need to submit it by 8:30 via the same link. Okay, let me know if you have any issues in opening the link or in submitting your documents. Okay, because if you can't do that, then I will accept a different way. But otherwise, I want you guys to submit through Google Form because I will have the date and time by which you actually submit your tutorial. Okay, again, this tutorial counts 5% towards your continuous assessment. Can I open the submission link? Oh, perhaps I still have it locked.
It shows that it can be only opened by the owner.
Okay. So let me see. Yes, it can only open by the owner. Is it in Google Form or in Spectrum?
Doctor, the Google form says that we need permission from the owner.
To open the template or to open the form?
To open the form itself.
Okay, let me check here. I think this is because I have not opened it. I didn't open for submission. Responses. I'm accepting responses. Oh, it's just because you are not using your Syswa mail, but I've already turned it off. Okay, so you should be able to just refresh and reopen the file. You should be able to download it. If you can't, let me know. Okay. So the instruction is very easy. Briefly discuss about the degasser module. So you can either use the information that I've talked about in this lecture, or you can just dig in some other information and just write it down. Okay. If you and another question is, if you're an engineer developing a degasser module, how can you ensure solvent have enough time to spend inside the module to ensure the gases are below saturation point to avoid bubbling? Okay, so that's the general instruction. So one is focused on the degasser module, and the second one is, is on how do you ensure that the solvent have enough time. Okay, so you need to definitely answer this. So how I will mark is by just reading through your submission and then particularly focusing on this. Oops. Oh, keeps on crashing. Sorry, my iPad keeps on crashing. And particularly focusing on how and on the question that I've highlighted in red, which is basically says, how do you ensure solvent have enough time spent inside the module? Okay, I will take a picture of the tutorial section and I will post it in the WhatsApp group in case you didn't have time to actually read through everything. Okay, so you can check it out on WhatsApp group. I've posted the tutorial there. It's a free tutorial. You can discuss. It's fine. It's not individual if you want to discuss. Say, for example, I'm not sure if there's any husband and wife in this group, so you can discuss. No issues. Okay? You can even discuss in your WhatsApp group if you want. Yes, Jayshree.
Well, I can't edit the tutorial sheet, the template.
So download it.
Okay.
Yeah. So you cannot just simply edit it. So you need to download first and then just type it.
All right. Okay.
Okay. I think that's all from me. Any question before we stop? Anyone? No? Okay. So that's all from me. Thank you. And we'll see you guys again next week. Okay, don't forget to sign in for your attendance and the submission. So there's 2 tasks. All right, thank you.
Thank you, Doctor.
Thank you, Doctor.